afternoon, everyone. Thank you for joining us for this seminar by Dr. Shirin Noei, one of our new faculty who joined us this fall. She's a research assistant professor at the Center for Energy Systems Research, or CSER. She received her Ph.D. just recently, this August, in transportation engineering from University of Florida. And she's been working in the area of transportation for some time. She was involved as a research assistant on 6 Florida Department of Transportation funded projects. And she has published her research mostly regarding connected automated vehicles, cyber physical systems, control system, and traffic operations. Her talk today will be on longitudinal dynamics in traffic microsimulation. I know that any of us that have suffered sitting in traffic would appreciate any work done in that area. So as I've mentioned earlier, this session is being recorded and will be posted on our website or our YouTube channel rather. Dr. Noei will take questions at the end of her talk. And one of the things that I wanted to mention, I noticed just a few days ago that I think she has started a new chapter, for a student chapter for women in transportation. So that's pretty exciting for us. And with that, I'm going to turn it over to Dr. Noei and look forward to her presentation.
Thank you so much, Dr. Motawalli, for introducing me. Good afternoon, everyone. I hope you and your family are staying healthy and safe during these uncertain and unprecedented times. As Dr. Motawalli introduced me, my name is Shirin Noei. I recently joined Tennessee Tech as a research assistant professor at the Center for Energy Systems Research, called CSER. This is an interdisciplinary center engaged in research on a smart grid, resilient infrastructure, and wireless power mainly. So I'm just go through the introductions. Society of Automotive Engineers defines 6 levels for driving automation. At level 0 driving automation, a driver performs entire dynamic driving tasks. At level 1 driving automation, driver assistance systems execute either longitudinal or lateral vehicle motion control subtasks, but not both simultaneously, and driver performs remaining dynamic driving tasks. At level 2 driving automation, driver assistance systems execute longitudinal and lateral vehicle motion control subtasks at the same time, and driver performs remaining dynamic driving tasks. SAE defines levels 1 and 2 automated vehicles, conventional vehicles. At levels 3, 4, and 5 driving automation, automated driving systems perform entire dynamic driving tasks. Levels 3, 4, and 5 are called automated vehicles, vehicles dedicated to automated driving systems. Dynamic driving tasks are real-time operational, including longitudinal and lateral vehicle motion control, and tactical, including object and event detection, recognition, classification, and response preparation functions required to operate a vehicle. Driver, vehicle, and environment are the most critical reasons attributed to 94%, 2%, and 2% of crashes, respectively. So you can guess that delegating dynamic driving tasks from a driver to automated driving systems, which represent levels 3, 4, and 5 driving automation, can eliminate 94% of crashes attributed to driver errors. We call level 5 automated vehicles autonomous vehicles. Cooperative driving automation is a new chapter in transportation engineering field. Cooperative driving automation means that vehicles dedicated to automated driving systems use vehicle-to-vehicle communication to cooperate with each other, with the vehicles, with their surrounding vehicles. What is the intent? The intent is to enhance dynamic driving task performance, safety, and traffic operations. As you can see in the figure that I have demonstrated here, vehicles equipped with cooperative automated driving systems can follow their leaders at shorter gaps and with less variation in acceleration and deceleration compared to vehicles dedicated to automated driving systems. Longitudinal controllers control accelerations and decelerations using throttle and brake inputs to maintain a constant distance gap in a platoon, such as truck platooning, or a constant time gap in a string, such as adaptive cruise control and cooperative adaptive cruise control. So when I'm talking about longitudinal control functions, I'm talking about something like adaptive cruise control and cooperative adaptive cruise control. But adaptive cruise control and cooperative adaptive cruise control are for only levels 1 and 2 automated vehicles, not levels 3, 4, and 5 automated vehicles. Commanded accelerations and decelerations are automatically confined to maximum accelerations and maximum decelerations specific to vehicle properties, road conditions, speed, and operation mode. Longitudinal controller coefficients in this research are those proportional, integral, and derivative gains that can be tuned to achieve desired performance, which can be, for example, maximizing throughput without compromising safety or string stability. In this research, vehicle dynamics is incorporated into minimum safety stance gap, maximum acceleration, maximum deceleration for conventional vehicles, and minimum safety stance gap controller coefficients, maximum acceleration, and maximum decelerations for vehicles dedicated to automated driving systems, which we call them vehicles in automated mode, and vehicles equipped with cooperative automated driving systems, which we call them vehicles in cooperative automated mode. So what is the problem here? The problem is that conventional traffic macrosimulation tools, or you can say conventional simulation tools such as VSIM and AIMSON, automatically confine these accelerations and decelerations to constant or estimated maximum accelerations and maximum decelerations, and rely on constant distance gaps and time gaps to simulate longitudinal control for automated vehicles in a platoon or a string. So when you want to simulate a longitudinal control functions such as adaptive cruise control or cooperative adaptive cruise control, you have to input all of these longitudinal control variables. So it's not like that, like the cooperative adaptive cruise control in real world, that they calculate all of these variables by themselves. So, for example, VSIM empirically estimates maximum acceleration and maximum deceleration based on the speed, or AIMSON assumes a constant maximum acceleration and maximum deceleration as default, or MidSim uses a constant maximum acceleration and maximum deceleration for each speed range, and all require user inputs for distance gap, time gap, and controller coefficients to simulate vehicles, automated vehicles in a platoon or a string. This research, what does it do? It incorporates driver characteristics, engine, transmission, and drivetrain properties, aerodynamic resistance, rolling resistance, grade resistance, speed, and operation mode, which we all call them, overall, we call them vehicle dynamics, into calculating maximum acceleration, maximum deceleration, minimum safety stance gap, minimum safe time gap, and longitudinal controller coefficients, which I call them longitudinal control variables in the rest of this presentation. So how we calculate, how we incorporate vehicle dynamics into a traffic macrosimulation tool. Currently, none of traffic macrosimulation tools is able to model vehicle dynamics. So what we do, for example, to calculate maximum acceleration, we adopted the model that has been developed by Dr. Washburn. Dr. Washburn at the University of Florida was the first one that introduced maximum acceleration in a traffic macrosimulation tool. This traffic macrosimulation tool is called SWISIM. And for example, I can say I personally developed maximum deceleration, minimum safety stance gap, minimum safe time gap by myself, and incorporated them into a new traffic macrosimulation tool. Maximum deceleration is calculated based on maximum braking force, aerodynamic resistance, rolling resistance, grade resistance, and mass. Minimum safe distance gap and minimum safe time gap are calculated based on sensing delay for conventional vehicles and vehicles dedicated to automated driving systems, and using communication delay for vehicles dedicated equipped with cooperative automated driving systems, speed, aerodynamic resistance, rolling resistance, grade resistance, and maximum deceleration. I don't want to go through the equations more in detail, and you can find them in my recent publication at Transportation Research Part C. Regarding vehicle generation, because in traffic microsimulation tool, you have to generate vehicles and then simulate the interactions between these vehicles and their surrounding environment. How we generate vehicles? Regarding a vehicle dispatching model for our traffic microsimulation tool, we assume that entry headways follow a shifted negative exponential distribution with distribution parameter calculated based on flow rate and minimum entry headway. So it's based on a random distributions. And our customized traffic microsimulation tool contains 10 driver types. We have some modules. One of the modules is driver, the other one is vehicle, and the other one is operating mode. Regarding driver module, we have 10 driver types, ranging from type 1, which is the most conservative driver, to type 10, which is the most aggressive driver. Treating drivers, vehicles, and operating modes as distinct objects so that users can customize vehicle and driver characteristics separately. Conventional vehicles are assumed to have two-dimensional improved intelligent driver vehicle following model, which is a very well-known vehicle following model. But what we did, we considered driver characteristics, physical and powertrain properties, and resistance forces in calculating minimum safety stance gap, speed, maximum acceleration, and maximum deceleration. So we adopted a vehicle following model that is usually what the vehicle following model that people in transportation engineering use, but we modified them based on modified it based on vehicle dynamics. Two-dimensional improved intelligent driver model is easier to be calibrated and demonstrates a more stable performance compared to Wiedemann model, which is the vehicle following model used in BSIM. BSIM is a very well-known traffic microsimulation tool. So consider 10 passenger car models, a single unit truck, an intermediate semi-trailer, an interested semi-trailer, and a double semi-trailer. What we do in our traffic microsimulation tools, we have implemented vehicle dynamics models for 10 passenger car models and 4 truck configurations. We can include more, but these 4 vehicle models, we had data for these 14 vehicle models. We consider them over 2 driving schedules. One of them is US 06 and the other one is Cycle D driving schedules. These 2 driving schedules, we assumed them to be a reference speed profile for our leader. And they are designed to test vehicles with aggressive driving behavior. So we wanted to test them in 2 driving schedules that are designed for aggressive driving behavior to make sure that we can capture all of the range of the vehicle dynamics model. All the results in the upcoming slides are calculated by taking the average of 20 replications for each scenario to make sure that, because vehicles are generated randomly, we use 20 replications to make sure that we capture all of the vehicle models with all of the driver characteristics and vehicle dynamics models. So we could capture more, but we did some trial and error and we found that 20 is a reasonable number. Before going through the results, I wanted to just explain that maximum acceleration, maximum deceleration, minimum safety stance gap, and minimum safe time gap all have a dynamic model with a minimum and maximum values. Maximum values for these dynamic models are called peak values for the rest of this presentation. Results show that in manual mode, as you can see here, it's not just a constant maximum acceleration or a constant maximum deceleration. It's a dynamic model. They have dynamic model. So it changes during the course of the driving schedule. Maximum acceleration is sensitive to vehicle model, vehicle classification, and speed. For example, maximum acceleration ranges from 6.7 to 9.5 feet per second square for passenger cars and 4.7 to 7 feet per second square for trucks. Passenger cars have on average 1.6 times higher maximum acceleration than trucks. Vehicles more frequently reach their peak maximum acceleration at higher speeds. Peak maximum acceleration is not sensitive to driver characteristics and speed. On average, vehicles have equal peak maximum acceleration at high and low speeds. Regarding maximum deceleration, the same. It has a dynamic model, but has less variation compared with maximum acceleration. Maximum deceleration is also sensitive to vehicle model, vehicle classification, and speed. For example, maximum deceleration ranges from 24.6 to 27.9 feet per second square for passenger cars and 19.4 to 26.2 feet per second square for trucks. Passenger cars have on average 1.2 times higher maximum deceleration compared to trucks, and on average, vehicles have higher maximum deceleration at higher speed. However, peak maximum deceleration is not sensitive to driver characteristics. Regarding minimum safety stance gap, I want to give you a hint that maximum acceleration and maximum deceleration are not sensitive to operating mode. It means that whether vehicle is driving in manual mode or in automated mode or in cooperative automated mode, it has the same maximum acceleration and maximum deceleration value, because these two variables are only sensitive to the vehicle properties and vehicle dynamics and should not change with the operating mode. But regarding minimum safety stance gap and minimum safe time gap, definitely they change with operating mode. What does it mean? In manual mode, minimum safety stance gap is sensitive to driver characteristics, vehicle model, vehicle classification, and speed. Minimum safety stance gap ranges from 80.4 to 225.8 feet for passenger cars and 89.8 to 336 feet for trucks. But if you do literature in transportation engineering papers, you see that they assume very lower minimum safety stance gap, like I think 10 feet or something like that, because they don't consider vehicle dynamics. At very high speed, they should vehicles should maintain higher minimum safety stance, higher distance gap. And if we assume a constant value for minimum safety stance gap, we should definitely consider very higher, longer distance gap. Trucks require on average 1.7 times longer minimum safety stance gap at higher speed and 1.3 times longer minimum safety stance gap at lower speed compared to passenger cars. Vehicles require on average 2.1 times longer minimum safety stance gap at higher speed. You might think that why we need all these numbers. They are very useful in designing adaptive cruise control and cooperative adaptive cruise control functions, because people just assume random numbers when they want to design an automated longitudinal control functions, and they don't look at traffic conditions, speed, driver characteristics, vehicle dynamics, and if they want to just assume constant values, they can use these numbers. But if they want to use dynamic values, which what we recommend for a traffic macrosimulation tool, they can use our traffic macrosimulation tool, or they can incorporate our proposed models into their traffic macrosimulation tool. Regarding minimum safe time gap, I can say that minimum safe time gap is sensitive to driver characteristics, vehicle model, vehicle classification, and speed. Minimum safe time gap ranges from 1.8 to 3.4 seconds for passenger cars and 1.8 to 5.5 for trucks. Trucks require on average 1.9 times longer minimum safety stance gap at higher speeds compared to passenger cars, and vehicles require on average 1.6 times higher minimum safe time gap at higher speeds. In three situations, automated longitudinal control function, which is very similar to adaptive cruise control, is activated. That is when an automated, a vehicle dedicated to automated driving system approaches a vehicle or a vehicle in dedicated to automated driving system is equipped with cooperative automated driving system and approaches a vehicle with the same characteristics. Or there is a significant discrepancy between onboard sensor measurements and V2V transmitted messages. When no leader is detected, definitely cruise control is activated. Cruise control in this scene can be simulated as the first equation, but with empirically estimated maximum acceleration and maximum deceleration values. Adaptive cruise control in this scene can be simulated as the second equation, but with empirically estimated maximum acceleration, maximum deceleration, constant time gap, and constant controller coefficients. Let's consider how we design this longitudinal control function. Let's consider two transfer functions, h and g. H is the closed-loop transfer function. Excluding a strict left half plane zero from H results in the second equation, which is g. Step response of G has lower rise time, higher overshoot, not significantly different settling time, lower peak time, and consequently not significantly different distance traveled during overshoot compared to step response of H. Distance traveled during overshoot, which is the shaded area in the figure, can be calculated based on critical time, rise time, peak speed, and later speed. Critical time is the shortest time taken for the step response to reach its peak value, and rise time is the time taken for the step response to rise from 1.9 to 0.9 of its final value. Distance traveled during overshoot should be less than or equal to minimum safe distance gap during acceleration, and settling time should be less than or equal to minimum safe time gap during deceleration. Settling time is the shortest time taken for a step response to enter a band of plus or minus 10% of its final value and remain in that band thereafter. These two conditions should be satisfied in order to maximize throughput without compromising safety, because usually in traffic macrosimulation tools, people just assume constant controller coefficients, so they cannot ensure that they can maximize throughput without compromising safety. Consider 14 vehicle models. Again, follow a 2006 Honda Civic on automated mode over US 06 and cyclically driving schedules, assuming vehicles drive in a single lane and there is no cut-in or cut-out maneuvers, because we just want to focus on longitudinal control functions, not lateral control functions. So we completely excluded cut-in and cut-out maneuvers. Regarding maximum acceleration, I can tell you the same results. So in automated mode, we have the same maximum acceleration and maximum deceleration results that I don't want to go through these details. But regarding minimum safe distance gap, definitely we have very shorter distance gap. Minimum safe distance gap is sensitive to vehicle model, vehicle classification, and speed. Minimum safe distance gap ranges from 42.4 to 172.6 feet for passenger cars and 49.8 to 276.1 feet for trucks. Trucks require on average 1.9 times longer minimum safe distance gap at higher speed and 1.5 times longer minimum safe distance gap at lower speed. Compared to passenger cars, vehicles require on average 2.6 times longer minimum safe distance gap at higher speeds. Regarding the same with minimum safe time gap, it is sensitive to vehicle model, vehicle classification, and speed. And again, we require very shorter time gap compared to vehicles in manual mode. Minimum safe time gap ranges from 1.3 to 2.5 seconds for passenger cars and 1.3 to 4.7 seconds for trucks. Trucks require an average 2 times longer minimum safe time gap at higher speed compared to passenger cars, and vehicles require an average 1.6 times higher minimum safe time gap at higher speed. Conventional traffic microsimulation tools do not provide a platform to simulate vehicles in a contested environment. What do we mean by contested environment? It is an environment that hacker can hack the vehicle, can hack the communication channels between vehicles. Our customized traffic microsimulation tool can simulate vehicles in uncontested and contested environments, assuming distance gap and speed are prone to measurement noise and process noise, and received accelerations are prone to measurement noise, process noise, natural fault, and malicious fault. Malicious fault we mean by like data falsification attack is one kind of malicious fault. Conventional fault detection methods are model-driven or data-driven. Model-driven methods such as Kalman filter, which we use in this research, require plant model and are more accurate and computationally intensive compared to data-driven models like neural network, for example. Data-driven methods required measure inputs and outputs under normal and faulty conditions to drive plant model. Data-driven methods are mostly suitable for nonlinear systems. In this research, we detect fault using Kalman filter. When an automated vehicle with vehicle-to-vehicle communications approaches another vehicle with vehicle-to-vehicle communications, connected longitudinal control similar to cooperative adaptive cruise control is activated. When no leader is detected, definitely cruise control is activated. Cooperative adaptive cruise control in BSIM and AIMSON are modeled as the second equation, but with empirically estimated and constant maximum accelerations and maximum decelerations, constant time gaps, and constant controller coefficients. Kalman filter is used to estimate states, which are distance gap, speed, and acceleration with minimum error. Distance gap and speed are known states, and acceleration is an unknown state. Unknown inputs are used to model fault, uncertainty, and noise with unknown statistics. The derivation of these equations to estimate unknown states, and unknown inputs are discussed extensively in our submitted paper to IEEE transactions on ITS. So if you want to know the details of this equation, I can share it with you later. Again, consider the same situation, the same 14 vehicle models, but this time in cooperative automated mode. And we have assumed 1 feet per second square, 3 feet per second square, and 5 feet per second square malicious fault on transmitted accelerations, assuming again that vehicles drive in a single lane and there is no cut-in or cut-out maneuver. Results show that maximum acceleration, we have the same. So it doesn't matter that vehicles are operating in contested environment or not, we have the same maximum acceleration and maximum deceleration results. But what is acceleration error? Acceleration error is defined as acceleration under normal conditions minus acceleration 0.1 second before a crash occurs under faulty conditions. 0.1 because it's our simulation time step. Acceleration error is sensitive to vehicle model, vehicle classification, and fault magnitude, but not speed. Passenger cars have on average 1.1 times longer acceleration error at higher speeds and 1.2 times longer acceleration error at lower speeds compared to trucks. Vehicles have on average 4 times longer acceleration error under 3 feet per second square malicious fault and 6.1 times longer acceleration error under 5 feet per second square malicious fault compared to just under 1 feet per second square malicious fault. So it's definitely sensitive to the malicious fault magnitude. This acceleration error is very sensitive to the magnitude of malicious fault. The same regarding maximum deceleration, the results don't change, but yeah, Regarding minimum safety stance gap, as we mentioned, is sensitive to vehicle model, vehicle classification, speed, and fault magnitude. Minimum safety stance gap ranges from 11 to 125.9 feet for passenger cars and 10.2 to 230.7 feet for trucks. So if we are not in a contested environment, vehicles in cooperative automated mode definitely require very shorter distance gap compared to vehicles in automated mode or vehicles in manual mode. But because we have assumed that we are in a contested environment, definitely results are not as good as we assume. For example, most of the literature on cooperative driving automation, they claim that cooperative driving automation can increase efficiency or reduce number of crashes by this. For example, it can increase efficiency by 400%, or it can reduce number of crashes by 94%. But because we assume that vehicles operate in a contested environment, these results are not as good as what we assume. Regarding distance gap error is defined as distance gap under normal conditions minus distance gap 0.1 second before a crash occurs under faulty conditions. Distance gap error is sensitive to vehicle model, vehicle classification, speed, and fault magnitude. Passenger cars have on average 1.1 times longer distance gap error compared to trucks at lower speeds. Vehicles have on average 2.6 times longer distance gap error under 3 feet per second square malicious fault, and 3.8 times longer distance gap error under 5 feet per second square malicious fault compared to only 1 feet per second square malicious fault. So this distance gap error again is very sensitive to the malicious fault magnitude that usually people in transportation engineering field ignore it completely. Regarding minimum safety time gap, the same, but if I go, I can say almost the same. We require much shorter time gap compared to conventional vehicles and vehicles in automated mode. But if only we assume that vehicles operate in uncontested environments. So if we assume vehicles operate in contested environments, first let me define what is crash time. The time it takes till a crash occurs under malicious fault is sensitive to vehicle model, vehicle classification, speed, and fault magnitude. Passenger cars crash on average 2.7 times sooner compared to trucks at higher speeds, and 1.2 times sooner compared to trucks at lower speed if they operate in a contested environment. Vehicles crash on average 1.4 times sooner at lower speed, and vehicles crash on average 1.7 times sooner under 3 feet per second square and 5 feet per second square malicious fault compared to when only they operate under 1 feet per second square malicious fault. So at the end, we wanted to validate our model using a vehicle dynamics simulation tool that is TruckSim in this research. Our proposed maximum acceleration model is validated against an industry standard simulation tool called TruckSim for 53,000 pound and 80,000 pound interested semi-trailers under 0%, 2%, and 4% grades. 53,000 pound is based on Florida weight in motion data, and 80,000 pound is maximum legal load without a permit. So we wanted to validate our model under a very aggressive situation to make sure that we capture all of the conditions. Proposed maximum acceleration model is further used to calculate minimum acceleration distances required for 50,000 pound and 80,000 pound interested semi-trailers, accelerating from various initial speeds to reach various highway design speeds on 0%, 2%, and 4% grades. Studies show that recommended acceleration distances in literature are not sufficient to accommodate safe emerging speeds for trucks because they don't consider vehicle dynamics. Our results show that TruckSim produces most conservative acceleration distances for 53,000 pound interested semi-trailer And our customized traffic macrosimulation tool produces most conservative acceleration distances for 80,000-pound interest semi-trailers compared to the recommended values by AASHTO. We have validated our model in an F.D funded project, and if you are interested to know more about this validation process, I can share with you this F.D proposal project report. In conclusion, we can say that maximum acceleration, maximum deceleration, minimum safe distance gap, minimum safe time gap, distance gap error, and crash time, all of them, they are sensitive to driver characteristics, vehicle model, vehicle classification, speed, operation mode, and fault magnitude that people completely ignore them in their research. Peak maximum acceleration is not sensitive to driver characteristics, speed, operation mode, and fault magnitude, and acceleration error is sensitive to vehicle model, vehicle classification, and speed, but not to fault magnitude. Peak maximum deceleration is sensitive to driver characteristics and fault magnitude. And in manual mode, vehicles require on average 1.4 times longer distance gap than in automated mode and require 2.4 times longer distance gap than in cooperative automated mode. In manual mode, vehicles require on average 1.3 times longer time gap than in automated mode and require 1.7 times longer time gap than in cooperative automated mode. However, in this research, we only assume that drivers drive in a single lane and there is no lane change maneuver. While a lane change maneuver can temporarily affect vehicle following behaviors. For example, drivers speed up or slow down to align with acceptable gaps in target lanes or temporarily adopt shorter gaps after a lane change maneuver or after a vehicle merges in front. Future work can model other significant components underpinning a traffic macrosimulation tool, which are lane changing and gap acceptance models. Macroscopic measures in this research, which are distance headway and time headway, can be aggregated to macroscopic measures, which are density and flow. Future work can estimate macroscopic benefits associated with cooperative driving automation, which is increased in roadway capacity under various market penetrations for vehicles dedicated to automated driving systems or vehicles equipped with cooperative automated driving systems. Most common cyber attacks can be modeled as faults, such as data falsification and spoofing attacks, or time delays, such as denial of service attack. Cyber attacks in this research were modeled only as fault. Future work definitely can model cyber attack as fault or time delay. Conventional fault-resilient longitudinal controllers are model-driven, as I mentioned, or data-driven, potentially sacrificing accuracy or simulation speed. Because model-driven methods are accurate, whereas data-driven methods are fast, future work can detect faults with model-driven and data-driven methods combined to optimize accuracy and simulation speed. To compensate the effects of cyber attack on distance gap, future work can design an adaptive controller to increase distance gaps in proportion to the cyber attack magnitude. At the end, I really appreciate that you took the time and participate in this presentation. I would be more than happy to answer any questions or address any concerns that you might have. Thank you.
Well, thank you very much, Dr. Noei, for that interesting presentation. And we have quite a bit of time for questions and answers by audience. So if you would like to ask a question, simply turn on your microphone, raise your hand, turn on your video, however works, and we will recognize you. As everyone is thinking, let me ask a couple questions to get us going. I'm familiar with the US 06 cycle,
Yes.
but not with, I think it was D, cycle D.
Yes, cycle D, yeah.
Could you describe that?
Yes, cycle D driving, US 06 or US 06, as you mentioned, both of them, US 06 and cycle D driving schedules are environmental protection agencies driving a schedule to test vehicle emissions models, vehicle emissions. US 06 is mainly used to test passenger cars, and cyclically driving schedule is mainly used to test heavy vehicles like trucks. And definitely it has a lower average speed, lower acceleration. Um, so yeah, it's completely the same as US 06, but it's just designed to test trucks.
I see. So the other question, you described it in the beginning, level 1 and 2, and then 3, 4, 5.
Yes.
And you mentioned that, so adaptive cruise control has been around for a few years now.
Yes.
But, that's still level 2. You said some of the lateral controls, like lane keep, I guess, or lane change,
Exactly.
uh, that now, does that begin to get into level 3, or in order to be level 3 you have to have cooperative? In other words, you have to have communications between vehicles to be able to do level 3, or is a lane change, for example, on top of lane keep, not just lane keep, but lane change, automatic lane change, is that a level 3 capability or automation?
Yes, as you mentioned, definitely if they automated vehicles, because level 3, 4, and 5, they are very high automated vehicles. So it would be really great if they can communicate with each other to do this task, lateral motion control with better performance. So I believe that if you want to go from level 2 to level 3 and you want to just focus on lateral control, there should be some kind of communication between vehicles in different lanes. But because we are just talking about adaptive cruise control, we are talking about vehicles in a platoon. So we can talk about vehicles, automated vehicles at level 1, 2, 3, 4, and 5. So it doesn't matter. But definitely, as you mentioned, if you want to consider lane changing maneuvers, we have to only consider automated vehicles equipped with cooperative automated driving systems. Yes.
Right, but at the moment though, so that would make them level 3, I guess, or 4, or whatever. But level 2, there are vehicles that have lane change capability
Yes.
by simply
Yeah.
turning on signal. So that's what I was getting at. Now the last question I'll ask, and then hopefully we'll have others asking questions, is that the list of vehicles that you had. I mean, they were rather old. So uh, I know that you were not obviously using those vehicles necessarily for any kind of automated driving, or vehicles with any level of, in fact, automation.
Exactly.
But so why not use some of the more recent vehicle models? Is that just the availability of the models?
Yeah, definitely we can use vehicles, definitely newer vehicle models. But when we were trying to test these models, we only had the vehicle powertrain information, like engine, drivetrain, and transmission models, only for these 14 vehicle models that I mentioned. I was working with Dr. Washburn, and Dr. Washburn was previously involved in a DOE project, and he only had the powertrain information of these 14 vehicles. Definitely, if we have powertrain properties of newer vehicles, we can implement it in model and see how they perform. So that's why we are trying to verify and validate all of our models in a vehicle dynamic simulation tools such as car sim, truck sim, or car maker and truck maker, to be able to verify our model with newer vehicle models. And yeah, we can also verify them with different truck configurations. So yeah, definitely in future work, I want to also use car maker to definitely verify my model with like I don't know, newer version of vehicles.
One model that does exist and was developed by Argonne National Lab is the autonomy, which does have certainly more up to date, but that's more for actually basically more of electric and hybrid electric vehicle design, essentially. Design of the component, not the component itself, but putting it together in terms of a powertrain and so on.
Mm-hmm.
And they have, but it's a different capability. I mean, I know for your applications for traffic simulations and so on, you need a different type of model.
Yes, we don't need that detailed vehicle dynamics models, but like torque, we need torque map, we need transmission models, some more, I can say macroscopic version or less detailed vehicle dynamics model compared to those that we can in like vehicle dynamics simulation tools car maker. They need very detailed information about vehicle powertrain properties, but our model needs like less detailed information.
Okay, I've asked way too many questions, so floor is open as such, virtual floor for questions by anyone else in the audience.
I have a quick question. All these factors and coefficients you mentioned, these are from simulations.
Yes.
Have those been verified experimentally?
Yes, those models I mentioned, they have been verified for 14 vehicle models, but as Dr. Mahajan said, they are not very up-to-date vehicle models. But we have validated those for 2 vehicle models, 2 truck configurations in truck sim. So they have been both validated and verified. Verified for 14 vehicle models and validated only for 2 vehicle models.
When you say validated experimentally?
Yes, because it's very hard to get real world data, but truck sim and car sim, they are truck sim, car maker, vehicle dynamic simulation tools are very accurate that most of the time we can use them to validate our model at the same time because the results are very close to actual vehicle performance, like real world data. So that's why I say we validated those using truck sim and verify them with our traffic macrosimulation tool and Dr. Washburn's traffic macrosimulation tool.
Okay, and then who are the prospective users? Can you name some?
Yes, yeah. Vehicle dynamic simulation tools such as car sim, truck sim, car maker, try maker, they are mainly used by mechanical engineers, I believe, because they are very accurate and they can only model a few vehicles. But our traffic macro simulation tool can be used mainly by transportation engineers, but not mechanical engineers, because they optimize accuracy and simulation speed to be able to simulate many vehicles at each simulation time step. And they are used to estimate macroscopic benefits and macroscopic benefits at this, and macroscopic benefits of cooperative automated vehicles and automated vehicles. For example, using this traffic macro simulation tool, transportation engineers are able to estimate safety and efficiency benefits of cooperative automated vehicles with with higher accuracy compared with conventional traffic macro simulation tools that currently exist. So I believe the main users are transportation engineers.
Okay, thank you.
You're welcome.
Other questions? All right, well, if there are no more questions, we can bring the session to end. And again, thank our speaker, Dr. Noei, for her presentation, and wish her best of luck as she develops her research.
Sure, thank you so much.
Thank you again, and have a good evening.
Thank you so much. Have a good day.